Hello everyone, we are from the 11th grade G class and we are Jill,
Ellie,
Doris.
Today, we'll be presenting a presentation from National Geographic's article, Changes in Matter, Physical vs. Chemical Changes. This is our table of contents. Our presentation is divided into 3 main sections.
What is a physical change?
What is a chemical change?
The gray area, where do they overlap? Changes in matter are all around us in our daily lives. Take a look at this picture. How many objects can you spot that involve scientific changes? Answer reveal. Here it is. Let's take a look from the top left to the bottom right. On the top left is the gray area of light bulbs. For traditional light bulbs like incandescent bulbs or LED bulbs, the light emission is a physical change. For special cases such as chemiluminescence bulbs, used in scientific experiments, if the light emission involves a chemical reaction, such as the burning of certain gases, the seemingly ordinary things in our daily lives often hide fascinating scientific principles. Today, we'll explain physical change, chemical change, the differences between physical and chemical changes, how to distinguish them.
First, we will introduce physical changes. The definition of a physical change is a physical change involves a change in the form, state of a substance, appearance, texture, shape, temperatures without altering its chemical composition. Key characteristics include no new substances are formed. The chemical composition of a substance remains unchanged, usually reversible. For example, when ice cubes are heated, they melt into water, and when frozen below 4 degrees, they turn back into ice. Although the form changes, the axis remains the same. This is the more classic example of a physical change. The iron used to press clothes, as mentioned earlier, is also a physical change. The heat from the iron alters the fabric's appearance by removing wrinkles, but it does not change the chemical structure of the material. This is a key characteristic of physical changes. This is an experiment and a short play we designed. Let's begin.
Jill, why are you still eating breakfast at this hour?
I overslept, but hey, after listening Doris talk about physical change, I just realized we can do an experience right now.
We're not in the lab. Can we really do that?
It's super simple. First, we have a piece of bread,
And
then I squeeze it. Even though its shape has changed, it's still a delicious piece of bread.
oh, I got it!
So yummy.
This is a perfect example of a physical change. Because the bread's appearance changes, but its composition remains the same.
As the experiment and the short play concludes, we move on to the second one, chemical change. A chemical change occurs when a substance undergoes a transformation that alters its chemical composition, resulting in the formation of one or more new substances. Chemical reactions are processes in which new substances are formed. These reactions are usually irreversible, meaning that the original substances cannot be easily recovered once they have reacted. During the chemical reaction, the chemical bonds between atoms are broken and reformed, leading to the creation of new compounds. Additionally, energy changeover accompany these reactions, either being absorbed or released in the form or heat. light, or other forms of energy. These characteristics are fundamental to understanding how chemical processes occur in nature and in various industrial applications. For example, cooking the beef belly, like the earlier example of roasted chicken, involves a chemical change. During the cooking process, heat causes the proteins and fats in the meat to undergo chemical reactions, which result in the formation of new substances, such as browning crust and different flavors. And it is irreversible, meaning you can't return the beef belly or roasted chicken to their original raw forms. Photosynthesis in plants is a chemical change as mentioned earlier. After absorbing sunlight, carbon dioxide, and a small amount of energy, plants produce glucose and oxygen. Let's take a look at photosynthesis.
During this process, which plants, algae, and some bacteria convert light energy into chemical energy stored in glucose, chlorophyll, in the plant cells of chloroplast absorb sunlight, and energy is used to convert carbon dioxide from the air and water from the solid into glucose, a form of stored energy. Here is the equation. 6 carbon dioxide plus 6 water and sunlight transfer to glucose and release 6 oxygen. Oxygen is released as byproduct. This chemical change is crucial for the plant's growth and survival, and it also plays a vital role in the Earth's growth and survival and in the Earth's oxygen cycle, supporting life for all organisms that rely on oxygen. Here's an experiment video about chemical reactions. Funny elephant toothpaste. Let's watch it together. Today, we're going to see the process of the elephant toothpaste experiment.
First, we add dish soap, hydrogen peroxide, and some food coloring.
Then, we add potassium iodide.
Wow! I looked it up. A concentrated hydrogen peroxide solution is mixed with dish soap. And then a catalyst is added to make the hydrogen peroxide decompose rapidly.
I know. Potassium iodide is commonly used as a catalyst.
With the help of the catalyst, the hydrogen peroxide quickly breaks down, releasing a large amount of oxygen. This oxygen rushes out of the container at high speed.
And is trapped by the dish soap, forming bubbles that combine into foam and erupt out like fountains.
Exactly. These reactions are all examples of the chemical changes we talked about earlier.
Oh, so that's how this works.
The biggest difference between physical change and chemical change is whether they are reversible or irreversible. Reversible. These are changes that can be undone. The object can go back to its original form. Irreversible. These are changes that can't be undone. The object completely changes or becomes another substance.
Water shows classic physical changes, which are reversible. For example, ice melts into water and refreezes, or water evaporates into vapor and condenses back into liquid. Even processes like sublimation, ice to vapor, and deposition, vapor to ice, can reverse, with the water's chemical composition, H2O, remaining unchanged.
As mentioned earlier, with beef patties and roasted chickens, the proteins in meats undergo chemical reactions during cooking. A clearer example is boiling an egg. The heat causes the proteins in the egg white to denature, breaking their original structure and forming a solid. This is a classic and irreversible chemical change.
Proteins are large molecules made out of amino acids, essential for various functions in the body. They help build and repair tissues, regulate body processes as hormones, support immunity by defending against infections, and provide energy when necessary. These vital macromolecules are found in both animal-based sources like meat, eggs, and dairy, and plant-based sources like beans, nuts, and tofu. And protein denaturation occurs when proteins lost their original structure and shape due to external factors like heat, acids, or chemicals. High temperatures can break the bonds maintaining the protein structure, while changes in pH, whether acidic or alkaline, can disrupt its shape and functionality. As a result, the protein unfolds and can no longer perform its original function. This change is often irreversible. A clear example of this process is cooking an egg, where the heat causes the egg white proteins to denature, turning them solid, a change that cannot be undone.
And the last content of our presentation, the gray area. The distinction between physical and chemical changes lies in whether a new substance is formed. However, in certain situations, the line between the two becomes blurred, creating a gray area. From a microscopic perspective, some changes appear purely physical, such as a change in state or shape. Yet, at the microscopic level, these processes may involve alternation in chemical bonds, hinting at underlying chemical changes. This difference in scale often challenges our understanding and classification of this phenomenon.
In the context of the gray area between physical and chemical changes, one example is the dissolution of sodium chloride in water. When sodium chloride, or common salt, dissolves in water, it may seem like a physical change because the salt dissociates into sodium ions and chloride ions without any new substances being created. The sodium chloride is still present, just in a different state from solid to aqueous form, and it can be recovered by evaporating the water. However, on a microscopic level, the process involves breaking the ionic bonds between sodium ions and chloride ions, which is a form of chemical interaction between the salts and the water molecules. Water molecules surround the individual ions, forming a solution. Although no new substance is permanently formed, the interaction between sodium chloride and water involves a reorganization of molecules, making it a gray area where both physical and chemical changes seem to coexist. Another example of the gray area is zinc and copper mixing to form brass. When zinc and copper are mixed, they form an oil-coated brass, which is a combination of these two metals. Initially, this might appear as a physical change because the individual metals are simply mixed together. However, brass has different properties than either zinc or copper on their own, like color, strength, and corrosion resistance. At the microscopic level, the atoms of zinc and copper are chemically bonded in a way that results in a new material. The process of alloying involves the formation of new chemical bonds between the metals, indicating a chemical change. The creation of brakes is thus a transition between physical and chemical changes. In both cases, the boundary between physical and chemical changes is not always clear-cut, demonstrating how processes can involve elements of both. In summary, changes in matter can be categorized as physical or chemical. Physical changes are typically reversible and involve changes in form, state, or appearance without alerting the substance's chemical composition. Examples include melting, freezing, and tearing.
On the other hand, chemical changes result in the formation of new substances through chemical reactions, often accompanied by energy changes such as heat, light, or gas production. These changes, like burning or rusting, are generally irreversible.
The key distinction between the two lies in identifying whether a new substance is formed, energy changes occur, or if the process is reversible. Understanding this difference helps classify and analyze changes in matter effectively.
Thank you all for your attention.
That concludes our presentation.
We hope you enjoyed our presentation and learned something new today.
Have a great day!